Hi students, today we are going to discuss about chapter 3, 12th physics, current electricity. So last two chapters we discussed about charges at rest, but now this chapter onwards we'll be dealing with charge in motion. So mainly what causes the charge to move? That concept we have already learned, that is potential difference. So if there is a higher potential here and there is a lower potential, then the charges will flow from higher to low, positive charges. So if there is a potential difference here V, then the charges will flow. And if the greater potential difference, a greater flow of charge is there. So the flow of charge can be characterized by a physical quantity, that is electric current intensity. Yeah, electric current we say. So the current is equal to dq by dt, the rate of flow of charge. So many charges are flowing means the current is greater, and very less number of charges are flowing in 1 second. So 10 coulomb per 1 second. In 1 second, if 10 coulomb is moving, it means that the current is 10 ampere. The unit is here ampere, SI unit, represented by a and milliampere, microampere. There are subunits for this. So this is actually the definition of electric current here. Electric current is simply how much charges are moving in just one second, and the cause behind the electric current is a potential difference. So in order to create a potential difference, we use battery, because battery has a positive terminal and a negative terminal. So it has a higher potential and a lower potential. So if you connect it with a battery, then these 2 points will be maintained at 2 different potentials. So charges can easily flow, and the charges carry what? The flow of charges cause the flow of energy, actually electrical energy. So let's go to the very famous formula, that is Ohm's law. We can just say that V and I are proportional, because when there is a greater potential difference and a very high potential, very low potential, the greater potential difference, then there is a greater flow of charge. So V and I are proportional. So V is equal to I, where R is called the resistance, and even you can write R is equal to rho L upon A, because this we have only learned in class 10th. Resistance of a conductor is directly proportional to its length, and also it is inversely proportional to area of cross section of the conductor. So if the conductor has conductor has an area of cross section, a small area of cross section or a big area of cross section, whatever, and it has a length L. So and it is made, maybe it's made of copper, it's made of magnet, it's made of some other material. So and the material is rho is here. So a special material has a different resistivity, and these all things we have learned in class 10. I'm not going to repeat it, because these are the basic things of current electricity. So but this class 12th physics, what we are going to focus is some vector quantities which involves in this Ohm's law. This is actually the scalar form of Ohm's law, V is equal to IR, but here we are going to derive vector form of Ohm's law with the help of the concept of drift velocity. So you have to revise the chapter 1 and 2 so that you can understand this concept. So what is the concept here? We are taking derivation of Ohm's law here. Derivation of Ohm's law using derivation of Ohm's law. So whatever I am teaching, you have to put down in a notebook, fair notebook, just like you have done in chapter 1 and chapter 2, and this chapter 3 also you have to write in a fair notebook, because when we will be having offline classes in the school, maybe 1 month later or whatever, according to the government norms, then I will check your copies from the beginning, because you have, when you watch these videos, you write down and practice, because unless you practice, you will not understand anything. So derivation of Ohm's law, and mainly we are going to derive the vector form of Ohm's law. So what is actually vector form of Ohm's law? V is equal to IR is a scalar form, and the vector form is J is equal to sigma E. That's a vector form. What is this J is equal to sigma E? Here J is actually current upon area and E is actually V upon L. This formula we have already learned in chapter 2. But this one is in a new quantity called current density. And we already know if there is a surface area like this and the current is moving, then the current passing through the area will be very less. But if the area is like this, then the current will pass through a larger area. So the orientation of the area, so area behaves like a vector quantity here, and this we already know in chapter 1. Chapter 1 we have discussed in last few derivations, especially Gauss law. So उसमें हमने E dot A करके एक फॉर्मूला का इस्तेमाल किया था और जो कि वो एरिया का इस्तेमाल कर रहे थे और एरिया वहां पे E dot A, E was a vector quantity and area was a vector quantity there. So E and area are vector quantities, and in the same way here also electric field is a vector quantity and the J is a vector quantity, and the magnitudes are given by this I upon A. It has a specific direction. So the current upon area has the same direction as actually the electric field. So how will you derive this? J is equal to sigma E using the concept of drift velocity. So using the concept of drift velocity. So for that we are going to derive first of all drift velocity. What do you mean by drift velocity of electrons? So let me explain you. Let me give you an example here. Suppose we take a conductor of area cross section A and length L connected to a cell. Yeah, applied a potential difference, what? V. A potential difference V is applied across this. So then, when a potential difference V is applied, so we already know V is equal to E into L. Yeah, E is equal to V upon L. So when E and V are interconnected, so if there is a potential difference, that is an electric field actually passing through this. So when there is an electric field passing through this, we know that the positive charges get moves in the direction of electric field, and the negative charges moves in the opposite direction of electric field. And for a conductor, what are the free charge carriers there? Conductor, metals are good conductors because they donate an electron. They have an extra electron in the outermost shell. And you learn in chemistry about the valence band and conduction band, and for metals, and both are mixed together, and in conduction band there are so many free electrons available. So these free electrons, they carry electrical energy. Yeah, they can carry electrical energy from one point to another. So here you see, when there is an electric field, when there is a potential difference applied, and this diagram is not required here. So when there is a potential difference applied across a conductor, then there is an electric field, and the electric field, in the electric field, the electrons will experience an opposite force, means in the opposite direction of electric field. So electrons इस तरह ड्रिफ्ट होना शुरू हो जाएगी, और लेकिन बात यह है कि जब आप इलेक्ट्रिक फील्ड अप्लाई नहीं भी करेंगे तो भी ये इलेक्ट्रॉन्स इधर उधर जा रहा है ना. कोई इलेक्ट्रॉन ऐसा, क्योंकि दे आर फ्री टू मूव, दे आर मूविंग ड्यू टू थर्मल एनर्जी, and they collide with an atom and come back, and collide with another atom and go, collide with another atom and come back in. But they have a random motion, and the net motion is zero. But if there is a potential difference applied, then we say that there is an electric field, and the force is equal to charge into electric field. And we can write F is equal to E into E, where E is a electron here. So an electron will experience this force, and due to this force, it will move in the opposite direction, minus E, opposite direction of electric field, and there is a net motion here. So that is what we are going to discuss over here. But we already know F is equal to ma by second law of motion. because the electron is a particle, so we can apply this formula. And now combining these two equations, what do we get? Ma is equal to minus EE, or acceleration is equal to minus EE upon m. So the electrons are accelerating and the velocity will change, but they will collide with an atom, and again the velocity, there's a different velocity, and again it will accelerate. So let one consider an electron which is accelerating, and the final velocity is v1, initial velocity is u1, and the acceleration, and after a time t1 its velocity becomes v1. So initially it has a velocity u1 accelerating, and after acceleration, after a time t1, then the velocity is v1. Then it collides and entire velocity changes to u2, and then it accelerates, and after a time t2 the velocity becomes v2, and after a time t2 it collides, and the moment it collides with another atom, then again its velocity changes. So it goes on like to vn is equal to un plus atn. So what is the average velocity? That is our concept here. Drift velocity or average velocity. So average velocity of an electron with which it drifts is called actually drift velocity, or drift velocity is equal to, you can just add is equal, so these are all actually vector quantities, so you can add it. So when you add this all and divide it by n, you will get the average velocity. So I'm going to add it like v1, v1 I'm going to write u1 plus at1, v2 u2 plus at2, and dot un, or a t1 plus t2 dot tn, whole divided by n, and I can just put the whole divided by n separately according to mathematical concept. So here it becomes average of initial velocity. So this is the average of the velocities when it is not accelerating, and this is actually the acceleration cost. So here when it is not accelerating means when there is no electric field, the average velocity is 0. Even though it is moving here and there, the total velocity is 0 because it is not drifting, because unless you apply a potential difference, electrons cannot drift. Even though they may have a random motion and going from here and colliding and coming back. And this one a, and this t1 plus t2 plus dot tn, पहला कोलिशन के लिए t1 टाइम लगता है, फिर वो दूसरी बार किसी से कोलाइड होने के लिए t2 टाइम लगता है. सो अलग अलग कोलिशन के लिए अलग अलग टाइम लगता है. तो ये टाइम का एवरेज जो है इसको हम बोलते हैं रिलैक्सेशन टाइम, बिकॉज दिस इज अ टाइम between two successive collisions, average time. So this is average velocity, drift velocity is equal to a tau, and a you already know, so put this value here. So when you put the value here, you will get a is equal to ee and upon m. So vd is equal to ee upon m. So if the magnitude is, we write drift velocity, the magnitude of drift velocity is this. So negative anyway, and in a vector quantity negative will show the direction only, not the magnitude. So Vd जो है वो E tau upon m है, that is called drift velocity. So अभी आप Ohm's law derive कर सकते हैं. Ohm's law का स्केलर फॉर्म V = IR भी derive कर सकते हैं, और वेक्टर फॉर्म J = सिग्मा E भी आप derive कर सकते हैं. So ये जो Vd है, और ये Vd को कहीं ना कहीं हम यूज करेंगे, है ना, यूजिंग दिस ड्रिफ्ट वेलोसिटी ओनली वी आर गोइंग टू डिराइव ओम्स लॉ. सो इसको कहां पे हम डिराइव करेंगे, कहां पे हम यूज करेंगे, लेट मी एक्सप्लेन. सो इस कंडक्टर में आपने पोटेंशियल डिफरेंस अप्लाई किया है V, तो इसके अंदर एक करंट फ्लो होगी, एंड दैट इलेक्ट्रिक करंट का मेजरमेंट जो है वो I होगा. I इज इक्वल टू क्या है, Q अपॉन T, या डेल्टा Q अपॉन डेल्टा T. So what I'm going to find is I'm going to find delta Q here. So this is the same as the concept that we learned in class 11 in the chapter 13, kinetic theory of gases. So that is the same concept we are going to use here. In the whole volume of the conductor, the wire, the free electrons are available per unit volume be n. So n is equal to total number of free electrons divided by volume. So then total number of free electrons is equal to n, number density, we call it as number density. Number density means number of particles per unit volume, number of electrons per unit volume. So number density into volume will be the total number of particles. So what is the volume here? Area of cross section is A and the length is L, so volume is A into L. And what about then charge? Charge is equal to N into E, because one electron का charge E है तो N electron का charge N E होगी. So you can put the value of N here. So in this way, when we calculate this, the final answer for delta Q, you will get delta Q is equal to NALE. That's the value for delta Q. And if you put this equation in this equation 1, equation 2, putting in equation 2, you will get I is equal to NALE upon delta T, or you can write even T, Q upon T. So what is L upon T? Distance upon time. L upon T, distance upon time. Distance covered by the electron divided by time क्या होगा? Velocity होगी. Speed होगा. Drift velocity या speed. So here velocity लिख रहा हूँ मैं इसको, और ये जो फॉर्मूला है इसमें Vd का वैल्यू हमने पहले से ड्राइव कर रखा है. So from equation 1 we will put the value. So I is equal to NAE और Vd का वैल्यू आएगा E tau upon m. So ANE square E tau upon m, which is actually correct. So now you have derived current I is equal to something here, E into something. And I can be converted into I upon area is actually current density called J. So I am going to put it here directly into the vector form. I upon A is equal to NE square tau upon m into E. And I upon A is J is equal to NE square tau upon m into E. For a given material, N is a constant, E and M are already universal constant, and tau and N, tau is relaxation time and N is a available number of electrons, free electrons. So in vector notation I can write this one as sigma, where sigma is equal to NE square tau upon A. It's totally the quality of the material, speciality of the material, which is called conductivity of the material. So the conductivity of the material is this, and the reciprocal of this is called the reciprocal of this is called the resistivity of the material. So resistivity you can write M upon Ne square. So which is called resistivity of the material. And by solving this again and converting this J into I upon A and E into E is equal to V upon L, then you can go for the scalar form of Ohm's law too. But the main derivation is a vector form of Ohm's law. So here you get the qualities of resistivity, and the resistivity of a conductor depends on mainly the number of free electrons available and relaxation time. So it is different for conductors, semiconductors, and in conductors the number of free electrons are constant. If the temperature is increasing, decreasing, nothing is going to happen. But for a semiconductor, when the temperature increases, then the number of free electrons are increasing because of the two different bands present there, conduction band and valence band. So the electrons from valence band jump into the conduction band, absorbing thermal energy. So when you increase the temperature, more number of electrons are coming and the resistivity decreases for a semiconductor. Whereas for a conductor, the number of electrons are the constant, they are same. But the relaxation time it reduces because electrons get more energy and it moves faster, and the relaxation time is less, so due to which resistance increases for a conductor. So that is why conductor and semiconductor behavior is totally different in terms of resistivity. So if you make a graph, it will be like for a conductor it will be like this, increasing resistivity and temperature, and for a semiconductor resistivity and temperature it will be like this, decreasing resistivity. So the graphs are given in your textbook, so you have to learn the graphs from the textbooks. And there is one more topic that you have to buy from the textbook, because there is nothing to be explained specially for this, that is resistors. So standard resistors जो है, so normally resistors वही होता है जिसका resistance और resistivity थोड़ा सा considerable amount में है. So नॉर्मली अलॉयज का हम इस्तेमाल करते हैं रेसिस्टर्स के रूप में, जैसे कॉन्स्टेंटिन है, मैग्नेनिन है. सो ये सब स्टैंडर्ड रेसिस्टर में यूज होता है, बिकॉज इनकी जो ग्राफ अपन टेम्परेचर का ग्राफ बनते हैं, रेसिस्टिविटी और टेम्परेचर, ये ऑलमोस्ट सीधा होता है, मतलब दे डोंट हैव ए बिग वेरिएशन. For a conductor it is a big variation, and for a semiconductor also it is a big variation, but for a alloy the variation is very less. So maybe a straight line or maybe a little bit curved line, but it's a very small variation. So we say that the temperature coefficient for these alloys are almost a constant, and it is small. So small temperature constant is there. Let's talk about the limitations of Ohm's law. This Ohm's law is, the scalar form of Ohm's law is V is equal to IR, and the limitations of Ohm's law is only when you draw a graph for Ohm's law, it is like this, VR graph, VI graph, VI graph or IV graph. You can say IV graph is like this, still it is like this. IV graph. It is a straight line, but when there is a higher, greater potential difference, the graph is not obeyed. The graph bends. It is not a straight line. Non-linearity is there. And for semiconductor, the graph, behaves very differently. For a semiconductor, sometimes the graph is like this. Two different values are there for current. Yeah, for a single current there are two different potential difference there, and for a forward bias and for a reverse bias the things are totally different. Forward bias, reverse characteristics and forward characteristics for semiconductor. So this will deal anyway in chapter 14 only mainly, but one of the limitation of Ohm's law is this: for semiconductor, the Ohm's law is not so valid, because it is far from this graph, VI graph, for a normal conductor. Okay, so that's all about this resistors, and there is series combination of resistor and parallel combination of resistor explained. So what do you mean by series combination of resistor and parallel combination of resistor? So this you have already learned in class 10th, and the same topic I am going to teach you here. So the resistor, the symbol of a resistor is this. So I am going to use three different resistors, R1, R2 and R3. Series combination of these resistors. So there is an ammeter here, and it's not necessary to show all those things here, because we are going to derive something, and we are not going to use the actual values here. So there is a current flowing anyway through this, and you have to always show the direction of current. And there is different potential differences at these points, because this is two different points and this is another two different points and another two different points. The potential difference is V1, V2 and V3. And the overall potential difference, that is the cell's potential difference, that is V. So we are going to derive a relation for the equivalent value of the resistance here. So for a series combination, we already know the current is the same, but the potential difference is drops in three different resistors. So sum of the potential difference is equal to the total potential difference. By Ohm's law, V is equal to IR. So IR1 plus IR2 plus IR3, and V is equal to I into R1 plus R2 plus R3. And this I you take here, V upon I is equal to R1 plus R2 plus R3. And this V upon I, V is the overall potential difference and I is the overall current. So V upon I, according to Ohm's law, V upon I must be resistance. So this must be the equivalent resistance. So equivalent resistance R equivalent. So instead of this, I can put it like R equivalent is equal to R1 plus R2 plus R3. So that is a very simple situation here. In the same way, for a parallel combination of resistors. Parallel combination of resistors. So this is key actually, we call it as key, and this is a cell with a potential difference V, and R1, R2 and R3. So when there is a current I flows, at this junction the current will split I1, I2, I3, because three different pipelines, so the current will be different, but the potential difference is the same, because from the same point it is connected, and from the same point all the three are connected. So potential difference across all these three resistors will be the same, लेकिन इसके अंदर से जो करंट जा रहा है वो अलग अलग बढ़ जाएगी. सो करंट बढ़ रहा है तो टोटल करंट को मैं ऐसे लिख सकता हूँ I1 प्लस I2 प्लस I3, और अकॉर्डिंग टू ओम्स लॉ V इज इक्वल टू IR, और I को मैं लिख सकता हूँ V अपॉन R. सो I को अगर V अपॉन R लिखेंगे तो ये जो I1 है उसको V अपॉन R1 लिख सकते हैं, I2 को V अपॉन R2, सारे में V सेम रहेगा, V upon R3, and all this V you can take and put it here. So I upon V is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. And you see V upon R is I, then the reciprocal of this, or I should say V upon I is equal to R. So V upon I, here it is I upon V. तो V upon I का reciprocal करेंगे तो 1 upon R. So it is very clear, it is 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So this is R parallel and this is R series. So this concept you have already learned in class 10th. So the same concept is here. So the next topic that we will be dealing is resistivity, the temperature coefficient we have already discussed, and there is a formula to discuss, that is a rho is equal to rho naught into 1 plus alpha T minus T naught. So this formula shows how the resistivity varies with respect to temperature. And for a metal, for a conductor, so this alpha, the greater alpha, so there will be a greater variation of resistivity. And another formula we have already run, rho is equal to m upon ne square 2. So these two equations are important for numericals and concepts. So the next topic in this is internal resistance of a cell, and then series and parallel combination of a cell, and then we will go for Wheatstone bridge principle using Kirchhoff laws, and we have a meter bridge and we have a potentiometer here. So these are the few topics that I will be dealing in the next video. This is part 1. I am doing it right now. So there is a part 2, another part 2 maybe of 30 to 40 minutes video. So in that I will discuss about the next half part of the chapter, and with that I will finish the chapter. So you try to revise this derivations, concepts, and try to do numericals based on these formulas from the exercises.